Greetings, everyone. As we're getting settled here, folks are now just joining into our webinar. We'll give people an extra minute or so to log in and join us. We have a really fine webinar for you today, so looking forward to that. So just give us another minute or so, and we'll go ahead and get started. While we're waiting and admitting folks, I want to thank those of you who were with us in Providence last month. What a great conference we had, and we really appreciate your participation and contribution. There were a number of really excellent technical papers, one of which you'll be seeing today. But also we had some really fine panel sessions on some really interesting topics. And so we're going to build on that. And we're now deep into the preparations for the 2025 event. So I'll share a little bit more information with you at the end of the webinar. All right, well, why don't we go ahead and get started? Again, greetings. We have a large audience from all corners of the globe. So good morning, good afternoon, good evening. And to some of you, I see it's late into the evening. So appreciate you being with us. My name is Dave Cadu, and I'll be your moderator for today's event. I'm the CEO and director of IWCS. We will have a large audience today, and as an attendee, you'll remain in listen-only mode. But also, this webinar is being recorded, so we will post this webinar on our website and our YouTube channel for future viewing, or if you want to share it with your colleagues, that would be great. We encourage you to submit questions during the presentation using the chat panel. It should be on the right of your screen once you select chat. And after typing in your questions at the bottom, hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So our IWCS webinar series events is hosted and supported by the Cable and Connectivity Industry Forum. And today we welcome Thomas Schelling. He is the technology manager for wire and cable of Huber Advanced Materials out of Georgia in the USA. And again, this paper, Optimizing Fire Safety Assessments, the transition from LOI, limited oxygen index, to HRR, heat release rate. And it was a technical paper in Providence. So we appreciate Tom being with us. Tom is the technology manager for wire and cable for the Americas division of Huber Advanced Materials, specializing in non-halogen flame-retardant additive technologies. Before joining Huber in 2022, he spent over 20 years at Teknor Apex in various roles, including research and development for wire and cable applications. He holds a master's in science degree in plastics engineering from the University of Massachusetts at Lowell, and a Bachelor of Science degree in chemical engineering from the University of Maryland at College Park. Tom is also a member of our IWCS technical committee, and we really appreciate his contributions for both the conference as well as this excellent content. So Tom, thank you, and take it away.
Thank you very much, Dave, and thank you very much, everyone, for coming to attend this seminar on 2 days after our Thanksgiving holiday. Hope everyone had a great holiday. So getting right into it, today's webinar is about optimizing fire safety assessments, the transition from LOI to heat release rate. So I'm going to get started with an introduction of Huber Advanced Materials for our agenda, but then I'm going to go into the details of the presentation itself. So J.M. Huber, it's an old company. It's been around since 1883. It's family owned and has been family owned for over 140 years. It has operations in over 20 countries. It has over 5,000 employees and approximately $3 billion in annual revenue. So the GM Huber Corporation operates a diverse portfolio of businesses that each focus on different industries and applications. The Huber Engineered Materials Group, which is broken down into 3 different businesses, and I'm part of the Huber Advanced Materials Group that specializes in halogen-free, fire-retardant additives, specialty aluminas, organic matting agents, and thermal management solutions. But it also includes Huber Specialty Minerals, which mines, refines, and sells calcium carbonate, and Huber Agro Solutions, which develops and supplies agricultural nutrients. Additional businesses include Huber Engineered Woods that produces innovative building materials, including engineered wood products to enhance the performance and durability of structures. And following in suit with Huber's sustainability focus, Huber runs a Huber Resources Corporation, which manages sustainable forestry operations and provides forest certification services to ensure the responsible land management and timber production of the engineered woods business. So Huber Advanced Materials, also known as HAM, offers a number of brands that support the wire and cable industry. So we offer a full portfolio of halogen-free fire retardants from aluminum trihydrate that are of different types: ground ATH, fine precipitated hydrate, and surface treated ATH that are sold under the trade names of Hydrol, Martinol, Microl, and Hymod. We also sell various types of magnesium hydroxides, from premium synthetic MDH to technical grade synthetic MDH, and we certainly surface treat these materials as well under Magnafin, Zerogen, and Vertex trade names. We also offer an intumescent flame retardant technology that's of a nitrogen phosphorus type called Sapphire. And lastly, we offer smoke suppressants that are molybdate-based complexes, and they're reacted onto various substrates to enhance smoke suppression performance under the trade name ChemGuard. And we also have some ChemGuard grades now that are actually suitable for polyolefins as well. So on to the discussion of the day: LOI versus cone calorimetry. So cone calorimetry is recognized as the leading laboratory instrument for measuring the fire behavior of combustible materials. And for this reason, we thought it was important to relate it back to an older test that's been used in industry since it was introduced into commercial testing in the 1970s, is the limiting oxygen index. And this test measures the minimum oxygen concentration to sustain combustion of a material. It's popular for quality control for flame retardant compounds, particularly wire and cable compounds. It's simple, fast, consistent, cost effective. And over the years, it's been adapted to be widely used to screen FR compositions for large-scale flame tests. But there's a concern, and that has been in place for my entire career, that it's not always reliable for this. And that's why we wanted to relate it to the cone calorimetry test. So this is a comprehensive method for evaluating material flammability. It measures a number of parameters: time to ignition, heat release rate, smoke production, mass loss. It provides detailed insights into the fire behavior of a material. And most importantly, with this particular test, laboratory scale correlations with large scale flame test outcomes have been successfully developed. So that's why we're trying to make this relation here today. So continuing with this introduction here, a fire, as it develops, goes through different stages, from ignition to developing fire to fully developed fire. This illustration shows this as in terms of time versus temperature. And after ignition, the temperature changes they're driven by the heat release rate and heat release rate related factors. So by measuring the heat release rate curve of a material, the cone calorimeter allows for a comprehensive bench scale investigation of how a material will react during these different stages. So our goal here is to examine the correlation between LOI and the cone calorimeter heat release rate and heat release rate related parameters, specifically for some PVC and LSZH test series that will be presented here. So our aim is to assess LOI's reliability as predictor of flame spread, and really to, on a broader sense, evaluate whether LOI should be limited to quality control testing only, or is it suitable for a screening tool for research and development. So on to our testing summary. This is an illustration of the limiting oxygen index test itself, an explanation of the test methods that are used, ASTM D2863 and ISO 4589, which I think they're most commonly known as. To the left, you'll see the apparatus itself that introduces a mixture of controlled mixture of nitrogen and oxygen, from which the limiting oxygen index is determined, which is defined by this test as a material that maintains combustion for 3 minutes and or consumes a length of 5 centimeters of sample, expressed in the following equation here. So materials, in terms of LOI, combustible materials are materials that will actually will meet these conditions at oxygen concentrations at or less than ambient oxygen concentration, which is at 21% or less. Materials that are greater than 21% are classified as self-extinguishing. So this is a small scale test. As I mentioned before, it's easy to train someone very quickly to be efficient with this test. And this illustration is of the cone calorimeter test. So these are the governing test standards, ASTM E1354 and ISO 5660. It's a comprehensive laboratory scale method for evaluating the material flammability. It was developed by the U.S. National Bureau of Standards, that's now called NIST, or the National Institute of Standards and Technology. It is widely recognized as the leading instrument for measuring the fire behavior of combustible materials. And the cone calorimeter represents an important space in the fire testing science as the largest of the bench scale flame tests and one of the smallest of the large scale flame tests. So to the left, you'll see a photograph of a brand new they don't look like this after they've actually been put in service, but a nice, beautiful marketing photo of a cone calorimeter. And the illustration here shows the functional components of a cone calorimeter. So it's a dynamic fire test. It measures heat release rate, heat of combustion, mass loss rate, smoke production rate. It's also capable of measuring carbon monoxide and carbon dioxide generation as part of the test as well, in addition to the beginnings of ignition as well. So more complex test. So I'm going to be talking about a number of terms during the presentation, and I wanted to give you some reference to understand their meaning and why they're important. So the first is the table here shows time to ignition. This is the time when flaming ignition is first achieved over the entire sample surface for greater than 10 seconds. So I think it makes intuitive sense to most people that a material with a longer time to ignition is less of a fire threat because there's more time to escape. The heat release rate it's recorded in a cone calorimeter over time using the oxygen consumption principle. It's measured continuously during the test, and the heat release rate versus time curve, it does represent the total fire hazard threat from ignition to the fire intensity at different times and the extinction for a material. And it is the focus of comparison for LOI here. But there are other parameters that are used to assess a fire a threat of a fire. One is the peak heat release rate. This is the maximum value of this heat release rate versus time curve, and is considered by many as the primary driving force for the fire development and intensity. Another parameter that's commonly used is maximum average rate of heat emission, or MARI. And MARI, this is a little more complicated. We're starting to get into numerical evaluations of the heat release rate curve. So it's calculated by first determining an average rate of heat emission. So it's just creating a separate curve, and from that value, a maximum value is determined. It shows this calculation shows a reduced sensitivity to experimental variations in measurement noise, and it's considered by some to be more reliable alternative to peak heat release rate because of that. So MARI values are used, for example, to assign hazard classes in the harmonized European Railway Standard EN 45545. Some other important parameters: the total heat evolved. It's calculated as the integral of the heat release rate through the entire test, and it represents the fuel load of the sample in a fire. And some calculated parameters below are also becoming more commonly used. The fire performance index is actually calculated from two other parameters: time to ignition divided by the peak heat release rate, and its character. So materials that have high FPI indexes are considered difficult to ignite materials with low propensity for flame spread. So if you can picture the ratio, time to ignition in the numerator, if you have a large number there, that's flame resistant. And for once you actually have ignition, when the material finally does burn, you want it to have a small peak heat release rate. So a big number by a small number, essentially you'll see how large values do indicate a more flame resistant material. And the last one, fire growth rate, this one is used in Europe also as well for classification of building products under the single burning item EN 13823, I think it is. But it's a calculated parameter that's the maximum of the heat release rate divided by the time to that peak heat release rate. So ideally we want a low value here, similar to the peak heat release rate. I think the best way to understand this is if you think of two different materials that have the same peak heat release rate. If you have one of those materials that reaches that peak heat release rate much sooner, that material is a greater threat. People have less time to get out. The fire is going to consume the room quickly. The other sample that has the same peak heat release rate, if it happens at a much later time, it's safer. So that's the essence of interpretation of FGRA, or fire growth rate, and why we want that value to be low. So let's talk about the experimental formulations. So in the introduction, I mentioned that we're going to be talking about two different formulations series that we're going to compare. So a low smoke PVC material, and a low smoke zero halogen formula based on EVA and polyethylene. So this is the PVC formula, the low smoke PVC formulation series, and it's the reference material here is designated as PVC2. But I created, the objective here was to make variations of formulation 2 here that give a range of LOI values, so that I can compare them to the low smoke zero halogen formulations to follow, and give them a similar LOI range, and then we can meaningfully compare the LOI and the heat release rate results. So formula 1, 2, and 3 are variations of 2 that use different concentrations of Huber's hydrol 710 fine precipitated ATH. So it ranges from 90, 60, 30 PHR of ATH. And then going to formula 4 and 5, there are variations of formula 2 where the molybdate-based smoke suppressant is changed. So we're moving from ChemGuard 620 to ChemGuard 3001 to ChemGuard MZM, going to formulation 5, and moving from 3 to 6, 7, 8, and 9. Now I'm trying to really reduce the LOI. I'm taking out flame retardants one at a time. So going from 3 to 6, I'm taking out the zinc borate. Going from 6 to 7, I'm taking out the ChemGuard 620. Going from to 7 to 8, we're taking out the antimony trioxide, and finally to formula 9, a formulation that only uses 2 flame retardant plasticizers as the only flame retardants in the composition, besides the halogen that's already inherent in the PVC polymer itself as a fire retardant. Now, looking at the low smoke zero halogen formulations, two series have been created based on formula number 3, which is the reference formula here. Again, I was trying to create versions of formula 3 that range from a low to a high LOI. So going from formula 1 to 4, we're going from 53.5 to 68.5% ATH. So we're going to have a range of LOI values there. But similar to the reference that was cited in the paper, I also wanted to see if some of these flame retardant synergists would help. So replacing 5%, going from 4 to 5, or replacing 5% weight percent of the ATH with zinc borate. And going to formula 6, we're replacing 5% of the ATH with an organoclay. And finally, in formula 7, we're looking at a developmental ATH from Huber. And then for the MDH-based formulations, the basis is now not Martinol 104 LEO. It is now the Magnafin H5 high purity MDH. And I repeated the same experiment set, simply making that substitution there. So from 53.5 to 68% Magnafin H5. And then we looked at 5% zinc borate, organoclay, and a developmental MDH version in this case. So this, in a quick snapshot, I needed to make a quick assessment of the limiting oxygen index values of these materials. So in green, you'll see the PVC materials, And in the dashed blue test results here are the LSZH materials, and you'll see the LOI values are very similar. They range from 26.7 to 53 for the PVC materials, and from 29.8 to 45.7 for the LSZH materials. I would have loved a perfect overlap, but I felt like the overlap was still very good and would allow for meaningful comparison of these data sets. So our goal was to relate these LOI values to heat release rate, but this is a lot of data to review all at once. So to simplify the explanation and interpretation of the results, the LOI results were divided into smaller groupings for review and discussion. So I have a low LOI group that's from, pardon me, from 26.7 to 35.5. A medium LOI group from 38.6 to 41.8. And a high LOI group from 45.7 to 53%. So let's take a look at those, because we're going to discuss those qualitatively to get started with. So this is the low LOI group, the 26.7 to 35.5 LOI group. And 50 kilowatts per square meter was selected as the heat flux for testing here. This falls within a typical range of a developing fire from 20 to 60 kilowatts per square meter. And it's at the lower end of a range typical of a fully developed fire. So I wanted it to be a fairly high intensity for that purpose. I wanted it to represent a fire, but I also wanted the higher radiance rather than maybe a more commonly used heat flux of like 35 kilowatts per square meter, because we also get better test reproducibility about it. So anyway, the plots themselves, you'll see as I start going, I'm going to review the heat release rates of different groupings of the LOI samples. And the table to the right is going to show you the LOI, the time to ignition, peak heat release rate, the MARE, and the total heat evolved for each of these materials too. So the first three curves are of the LSZH materials that range from 53.5 up to 63.5% ATH. You can see that they show a progressive increase in LOI, and that as that occurs, we get some corresponding reductions in heat release rate. That makes sense, right? This would be supporting LOI being good for this. When we switch from ATH to MDH at 53.5 to 58.5%, you're going to see now we have higher LOI values and time to ignitions, but that the heat release rate is higher than the ATH at the same percent. So these are all LSZH materials. Looking at PVC number 9, which has the lowest LOI in the grouping. It has no solid flame retardants, only FR plasticizers. Even though some of these other materials have higher LOI values, it actually looks superior. Looking at formulation 8 and 7, which have 30 parts of ATH, for formulation 8, and formulation 7 has 30 parts of ATH plus an additional 5 parts of ATO, you'll see that the heat release rate is reduced even further. So the 30 parts of ATH is easily detected, even though when you're looking at formulation 9 and 8, the LOI values differ by less than 1%, but the heat release rate is dramatically different. Adding the antimony trioxide also dramatically increased the LOI and time to ignition, but looking at the yellow and blue together, they don't differentiate very well here. The time to ignition is higher, and you'll see also in this 300 to 500 second range, you can see the dip related to the ATO concentration, but it's not immediately apparent. So moving on to the medium LOI group from 38.2 to 41.8, this grouping has different chemistries that are all grouped together, but the reason I wanted to show them is the LOI values are very tight. It only ranges from 38.2 to 39.6, but the time to ignition ranges from 68 to 89 seconds. The peak heat release rate practically doubles, going from 106.7 to 205.6, and the total heat evolved ranges from 38 all the way to 70.9 megajoules per square meter. So LOI is not really doing a good job of showing the differentiation in flame performance in these materials here. Looking at the next set, this is showing LSZH formulations that are looking at the different flame retardant synergists that are added. So one of the formulations, formulation 4, In purple is the 68% HEH containing LSZH formulation. Formula 5 is replacing 5% with zinc borate. So formulation 5 is in black. It has a very slight reduction in heat release rate and slightly better. Looking at formula 6, which is in red, this is including the 5% organoclay. You'll see it's got a strong spike for peak heat release rate here, and it has a higher second peak later on. When we look at MDH containing formulations for a similar comparison, you'll see that the formulation was 63.5% MDH and 5% zinc borate in formulation 12, which is in blue, is one of the better performers here. But the formulation in gray with the organoclay shows the highest peak heat release rate early and a very strong peak later. So it's not showing the best performance here. And formulation 14, which uses the developmental MDH, also has excellent performance and a lower heat release rate value even than the zinc borate. And the last for comparison here in this grouping is the PVC formula 3 and 6. They include only 30 parts of ATH, 10 parts of ChemGuard 620, 5 parts of ATO, and 2 parts of zinc borate. Very difficult to tell these apart because the only difference between these two really is formulation 3 has 2 parts of zinc borate. You'll see it in the time to ignition. Formulation 3, the time to ignition goes up from 71 to 87. So that's picking up the results. But other than that, these samples look very, very close. And overall, you'll see they're actually far superior to the LSZH materials themselves, and they haven't even gotten very flame retardant yet, which brings us to our last grouping from 45.7 to 53. And you'll see that the highest grouping here for the LSZH material is formula LSZH 11, which has 68.5% MDH. It shows a significantly higher LOI over the other LSZH formulas, but it exhibits a lower time to ignition and higher peak heat release rate, MARE, and time to ignition over some of the ATH formulations. But let's look at the PVC formulations that are using the different ChemGuard materials and have the highest level of ATH as well. So formulation 2, which is the reference formula actually, it is showing a higher time to ignition, lower peak heat release rate, MARE, and time to ignition over LSZH 11. When we switch from the ChemGuard 620 to the MZM, we see a significant drop in the heat release rate as well. And the formulation with the highest LOI of the different molybdate-based series was the ChemGuard 3001. Also showed very good performance, but had a little higher second peak to the peak heat release rate. And PVC1, which had 90 parts of ATH, which should be our most flame retardant composition, is showing this. And it is the most flame retardant composition in the study. But it does look like the sample with the MZM here achieved almost the same performance with only 10 parts of additive versus 30 extra parts for the formulation 1 with 90 parts. So that is the qualitative comparison. So how well do they correlate with just in an aggregate way to the heat release rate related parameters? So this first graph is showing the peak heat release rate correlated to limiting oxygen index. And I broke this up into 2 ways. I wanted to see if we looked at only the LSZH materials, how well did they compare in red? How well, if we only correlated the data for PVC, how well were we able to model the data? And the last, if I looked at them all as an aggregate value, and I'm trying to look at LOI as an intrinsic property, how well does that correlate to the peak heat release rate? And to determine the degree of, or the quality of fit, I was using the coefficient of determination for each of the models to measure how accurately the calculated model predicts the data results. And you'll see the qualitative assessment of the plot shows that at lower LOI values ranging from approximately 26 to 40, there's a large variation in peak heat release rate for similar LOI values. For instance, if you look at 35 LOI here, there are 4 data points that are actually shown in this line here that range from, I think it's about 120 to 330. So in none of these cases is it well represented, but the correlation coefficient values themselves are significantly less than 1, indicating that the models are missing the variation in the test is not being represented by the model here at all. Looking at the MARI, or the maximum average rate of heat emission, they were plotted in this figure, yielding similar results to the peak heat release rate. However, the R-squared values were slightly improved here. This is likely due to the attenuation of the experimental noise through data averaging, in particular the R-squared valued for the PVC data set here. It's fairly high, but it's really not high enough for scientific. If any of you have done design of experiments, if you were asked to bet money on whether this model is going to pass a particular result, you still have about 21% of the data that's not being represented by the model here. So that's not ideal. Looking at correlation of LOI versus the total heat evolved, the results plotted in this figure show a strong correlation of LOI with total heat evolved for the PVC. So looking at this right off the bat, this is one of those aha moments when I was doing this paper. It did surprise me. I was like, wow, that's a pretty good correlation for the PVC. And the value was fairly high when we looked at the LSZH material by itself. But when you looked at them in aggregate, the correlation was like the worst in the entire set, really showing when you go from one chemistry to another, from PVC to LSZH, you cannot compare LOI of different chemistries at all. And this is actually showing that very well. So these, I actually was surprised by this. I thought most of it was going to be similar to some of the previous plots that we looked at. This plot now is correlating LOI versus the flame performance index. So interestingly, this figure shows that the best fit for LOI versus FPI is for PVC data, and it's an exponential model. But you'll see actually at the higher LOI values, and it may be because I don't have enough data here too, but the model is not fitting it very well at all. In contrast, the LSZH data still is the best fitting model I was able to find, was still a linear one, and the value is higher. And together, it still wasn't terrible, but again, it wasn't good enough. It's directionally accurate is what I would call it, but not the model's not good enough for accurate scientific prediction. And that result is similar here in this case when we're comparing the LOI versus the fire growth rate. Fairly high coefficients of determination, but still not enough for accurate scientific prediction. So this plot here shows a comparison of the coefficient of determination for the different cases, LOI versus peak heat release rate. Not very good at all. And if this is the primary parameter for looking at the threat of a material in a fire scenario, these are not good correlations for LOI to peak heat release rate, particularly when we're crossing chemistry here. LOI versus MARI, better with some data averaging, but still not very good. The interesting case here, PVC for total heat evolved, that I consider that a pretty good fit there. But again, looking at it across chemistries, the worst fit of them all. And we have some directional accuracy with LOI versus FPI and Figura here, but not good enough for scientific prediction here. And for the last section, I wanted to show some results of smoke production of these different materials. So as we're going, and some of these make intuitive sense. We're starting with our formulation that has the PVC formulation with 90 parts of ATH. We have a fairly low total smoke release value. And as we take out 30 parts of ATH, it gets a little worse. And when we take out 30 more, it gets worse, which is what we would expect. So looking at the next two formulas, we're looking at alternative ChemGuard chemistries for smoke suppression. So this is using ChemGuard 620, and now we're using the ChemGuard 3001. The smoke production rate gets a little lower, but the ChemGuard MZM significantly reduces the smoke production rate. Even compared to 10 parts of MZM, outperformed an additional 30 parts of ATH here. And as we take out different flame retardants, going from formula 3 to 6, we're taking out zinc borate. The smoke is a little bit reduced, oddly. And now we're taking out the ChemGuard 620, so some of the smoke suppression is getting reduced. And we're taking out the ATO. A lot of people say ATO creates smoke. In this case, you took it out and it got worse. So that's interesting. This last one is another one of those aha moments. We're going from 30 parts of ATH from this sample here to no ATH. And you'll see that even 30 parts of ATH dramatically reduced the smoke in this PVC formulation. So that was I knew it would reduce the smoke by adding it, but I didn't think it would be that much. But it's significant. Looking at the different LSZH formulas from 53.5 to 58.5 to 63.5 to 68.5, you'll see of HEH, you're going to see the smoke is getting lower and lower. Now we're adding, replacing 5% of the HEH with zinc borate, with the organoclay. Now, the organoclay wasn't a good actor from the peak heat release rate standpoint and the heat release rate curve, but it is a good actor here in smoke production. And then looking at the developmental ATH, that was the best one in the set. Repeating this study with MDH, you'll see that there's a steady progression of smoke reduction with higher concentrations of MDH. And on average, it looks like the MDH has lower smoke production on a percent by percent basis versus ATH. It doesn't look like the zinc borate or the organoclay has a significant improvement over just more MDH in this case, but using the developmental MDH does. So moving into the conclusions here. LOI versus heat release rate correlations from a qualitative comparison standpoint. Similar LOI compositions do yield varying HRR related heat release rate related curves. The poorest correlations were observed when comparing PVC versus LSZH data, and this does indicate that LOI, it is not an intrinsic property. Most frequent instances of the poor correlations were found in the lower LOI set from 26.7 to 35.5. When we looked at the regression analysis, the combined PVC plus LSZH data set, there is no correlation for peak heat release rate, MARI, or total heat evolved. A weak correlation was observed for FPI and FIGRA between 0.7 and 0.9. When we're looking at the chemistries individually now, PVC or LSZH, again, there's no correlation for peak heat release rate. There was a weak one for PVC and just none for LSZH materials. Total heat evolved, flame performance index, and FIGRA, there was a moderate to strong correlation. And got to mention that special case here of LOI versus total heat evolved for PVC. Really strong correlation there, which was a surprise. So the implications here, moderate correlations combined with the test simplicity and cost effectiveness, it helps explain why LOI has some popularity, because there's got to be, anyone who's worked in the industry for a long time in the flame retardant area has probably seen some data points now and again where you see LOI gave you the direction that ended up being important, but it doesn't do it reliably enough to be useful as a screening tool, in my opinion. And I think this data supports this. And so it's unreliable for predicting heat release rate and therefore large scale flame tests. From a material insight standpoint, Hydrol 710 and Martinol OL 104 LEO, ATH in PVC and LSZH formulas, they play a central role in these low smoke compositions. They're effective at proving LOI and heat release rate at 60 parts and above. There's no LOI enhancement at 30 PHR or below, but it's effective for heat release rate and total smoke reduction. And that was easily and dramatically observed in the cone calorimeter. The ChemGuard molybdate-based complexes in PVC, they are effective in increasing the LOI and reducing the heat release rate, not just suppressing the total smoke release. So the 3001 was most effective for increasing the LOI, and the ChemGuard MZM was the best for the lowest heat release rate and total smoke production. Antimony trioxide in PVC increases LOI, we all know that, but it also increases time to ignition, slightly reduced the total heat evolved, but there was no reduction in peak heat release rate or MARI. The zinc borate in PVC slightly increased the LOI, slightly increased the time to ignition, and the heat release rated terms remained similar. The Magnafin H5 MDH in the LSZH, it showed higher limiting oxygen index and time to ignition, lower total smoke release compared to the Martinol 104 LEO ATH. The 68.5% Magnafin H5 showed the highest of the LOI values of all the LSZH compositions, where the 104 LEO had lower heat release rate related results. And finally, the developmental hydrates, developmental ATH and MDH additives performed the best for the total smoke reduction. And overall, the MDH developmental grade performed the best. So I'd like to, in closing, express my sincere gratitude to the Huber Advanced Materials team, Pete Hull and Alex Iseroff, for their support in terms of time, facility, funding, and encouragement throughout this research. To Mr. Thomas Allen for his diligent work in our laboratories for preparing the samples and meticulously performing the testing that was presented in this paper. To Christian Panafin and Zara Fahimi and Keith Sorrell for their creation of the graphics and company informational slides, and for coordination support with IWCS, and to Dr. Paul Burgundy of Dow Wire and Cable for generously donating the EVA and maleic anhydride graft copolymers that were needed for this study. So with that, I say thank you very much, everyone. Any questions?
Tom, excellent presentation, and obviously a very important topic as we go forward, looking for more enhanced fire safety to go along with performance of various wire and cable constructions. So thank you very much. Curious in terms of sampling and using this technique, obviously you were focusing in on specific materials and looking at the material components, but can you make any correlations to cable materials, the matrix of cables, and perhaps, you know, granularizing cable designs and combined materials?
I can tell you what I've learned over the years, Dave, that you can't look at what we're looking at here at materials that will either be the insulation or jacketing on cable constructions, and it's only part of that construction. And if you look back at some of the literature, like last year, UL gave a presentation on their correlations with large-scale burn tests of cone calorimeter testing. And they weren't using plaques like I was using here. They were using cables. They were cutting up cables and they were putting in because they understand also that the other components in a cable construction are going to contribute to the fire test performance. But I will tell you this, I've had some success in the past and seen it where if you do what they did, you can actually use a cone calorimeter to correlate your materials results you get to large scale burn tests. So this is the approach I use is really for just assessing the materials themselves, but it's still definitely helpful in determining whether you're directionally helpful if you're going to be able to make improvements in your compositions.
And can you extrapolate in you know, with some uncertainty, but can you extrapolate the results that you have here for the PVC compounds, the halogen-free compounds, into the various vertical or horizontal flame tests for cables? Obviously, you know, we've got the CPD requirements, vertical flame, we've got the plenum, we have the riser. Is there a way to say, hey, this material would likely perform better in any of those tests?
I would say if you have significant industrial reference materials where you already have results from that large scale burn test, Dave, say you have a reference material and you test that alongside these, that's your guide rails. If I looked at the numbers just without those references, no, because I've done some testing in between different laboratories with different cone calorimeters too, and the results can be slightly different. You still need that reference material to do side-by-side comparison.
Right. What are the deviations of the limited oxygen index and the heat release rate data?
You mean what type of variation would I expect in the LOI test itself?
Yeah.
That's a good question. In my prior experience, you can, but from testing the same material over and over again, you could see variations of maybe 1.5%, maybe even 2%. But I can tell you some manufacturers have incorporated some rigorous testing algorithms for their LOI apparatus, and I won't mention them by name because it sounds too commercial, but there's companies out there that it'll make you spend extra time doing your testing, but you can get test results that are like plus or minus 0.5%. So if you do the test rigorously, you can get some fairly accurate test results. But I'll tell you, in most of my experience in industry, plus or minus 2% is about is about what you're going to get.
Yeah, that's fair. The configuration of the tests, horizontal configuration. Have you done any vertical configurations? Because, clearly dripping and char integrity are also important in addition to the other parameters like flame spread, things like that.
I'm going to give a shout out to Dr. Kang from UL on this. That's exactly what most of my testing experience has been with horizontal testing, where the radiant panel is, I mean, the radiant coils are radiating the heat downward and on a horizontal specimen. But you can, if I actually go to the, wait a minute, I'm going to go back to my slide that shows the illustration of the result of the cone calorimeter. Let me go to that. Where is it? Can you see my slide?
Yes.
Yeah, so you'll see that Dave is referencing. You don't have to set it up like this. You can set it up where the cone is projecting onto a vertical specimen. So UL in their paper last year at IWCS were testing cables for riser, and I believe it was for the EN 50399 for the CPR in Europe. He strung up cables in a vertical orientation similar to this. So I haven't done it, Dave, so I can't comment, but obviously that Dr. Kang was dedicated to this research, and he felt in that case his data required that be done. So
right.
it can it be significant? Yeah, oh yeah, it can be.
Sure. You've already shown the correlation between limited oxygen index and peak heat release rate. Have you done any correlations between the average heat release rate to limited oxygen index?
I didn't. I thought about looking at some other parameters like that, but I looking at the cone calorimeter related literature, the ones I focused on were the ones that I found predominantly were the ones that fire scientists were more concerned with. But I know that one is discussed periodically too.
Good. Okay. Do you have any data or sources showing the correlation of the cone results to wire testing besides the UL sources that you cited? I'm sure a lot of companies are doing this and a lot of entities are doing it, but do you have any other data or sources that we might reference?
Dr. Ed Weil did some research where he was comparing LOI to, I think it was the VW1 burn test as well,
right,
and seeing if there was a correlation there. So I can, off the top of my head, I know Dr. Weil had some results that he was presenting like that. And I think Dr. Gunter Bayer gave presentations where he was focused on LSZH materials and organoclay, but he was showing correlations with large-scale burn tests and organoclay. But did he focus on LOI? I don't think that he did. I don't think that he did.
No,
but
he didn't focus on LOI, but he has some excellent papers. For those of you who have not found them, I think they're the AMI Polymers and Cables Conference several years ago. Dr. Bayer had some great presentations. So that's an excellent source as well. Mm-hmm. Looking at the heat release rate curves, what reaction do you think is occurring during the second peak?
That's a great
what's
question.
Happening after you've reached the first peak, and then you're now evolving into something else?
When I've seen those results with the NFPA 262 burns and cables, in a case like that, I've usually believed it to be when the jacket has burned through and the internal core is now starting to burn. Seeing that additional peak when you're talking about looking at a solid piece of plastic, I think that's char failure, because a char form, one of the reasons for looking at some of the other synergists in the study is that a number of them are char formers, Dave. So how effective is your char at protecting material under it from continued combustion? How well does it endure the heat flux before you get burned through and a second peak? So I think it's a similar mechanism, similar to what's going on with the cable, is that you have a char. In the case of the cable, I think it's a total burn through of the jacket. In this case, I think it's a burn through of the char.
Good. What are the exact deviations in your results for the correlations? I mean, that's kind of a difficult question, but I think you already discussed deviations of, you know,
Yeah,
2%
yeah.
or so, but
So we didn't exactly do an ASTM, follow ASTM 1354 for the cone, which calls for two things: 3 specimens to be tested and also to have a retaining grid. We kind of have a belief that the retaining grid, in particular, if you have a sample that intermesses or has a growing char, you unnaturally break up that char. And in breaking up the char, as it's trying to, if you've seen what a grid looks like, and I'm sorry, I don't have a picture of one, but they're a grid that has little square openings to hold a specimen down. You don't want, if you're testing a truly intumescent material or a material that intermesses during combustion, it may expand greatly out of the sample holder and may actually damage the heating coils of a cone calorimeter. So there is a desire to protect the cone, but if you know the material doesn't do that, at least that much, you can actually get artificially poorer results by using the retaining grid. So and that doesn't happen with cables. There's nothing restraining it from expanding on the cables if it needs to intermess and protect the material. The other is we only tested 2, not 3, so a statistical comparison of 2 for the. We looked at them to make sure that they looked like they were very similar. So we qualitatively determined that the burn was similar. And we didn't really have to test any. Using the LOI, the repeatability, actually, we get a report from our limiting oxygen index apparatus that actually tells us the standard deviation. It's slightly different for each of them, but it's very low. Because in most cases, the LOI values were determined by 10 to 12 individual tests to actually determine what the LOI values are.
great. One last question. Can this test be used to compare relative flame performance of multiple material classes to each other? I know you had some charts there, obviously PVC and halogen free, but different material classes comparisons.
I don't think you can do it with LOI. I think this paper showed that that doesn't work. Using the cone calorimeter, I believe that you can. I believe that you can. And I think that's why there's international interest in the device as well, because of its capability to do that.
Great. Okay, well, we certainly appreciate all the questions and the participation from the attendees today. And most importantly, we thank Thomas for his very interesting and really relevant topic today. We learned a lot from the different comparisons and the use of a very important tool to measure the impacts of materials on fire performance. So please note the contact points for Thomas, his email here, if in case you want to reach out to him directly, and he will get the support of his Huber team as well to help respond to any questions that you might have. Each of our webinar series events are recorded, so you can go onto our IWCS.org website and our YouTube channel and find all of the webinars that have been presented over the last 5 to 6 years. So a lot of great content if you're looking for particular topics and information. This webinar will be posted probably within a few days or a week or so, and so you can share that with your colleagues. The IWCS webinar series events take place once or twice a month. And our next scheduled technical paper presentation webinar will be on Friday, December 13th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for that event. And also, please share these announcements with your colleagues so that they can sign up and participate in these very interesting events as well. Before we conclude, I do want to thank and share the list of our partner sponsors, including Huber Advanced Materials. We want to recognize their outstanding contributions to the IWCS Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global audience. So again, thank you to these leading suppliers in our industry for your support. And again, thank you to Huber. Do want to remind you, we are in full swing trying to prepare the concepts for the IWCS 2025 event in Pittsburgh, Pennsylvania, USA. It will be the last week in October. We really hope that you'll plan to attend and interact with the presenters and learn so much more on the trends and innovations going on in our industry. Please be aware that our call for papers is about to be launched. So please be thinking about submitting an abstract for all of your good work, your hard work that you and your company are achieving. And IWCS is an excellent forum for you to share that information and show your capability and the strong work that you're doing. So please be aware of that. Submitting an abstract is easy, sort of a one-page summary of what you want to present. So that'll be opening shortly. So again, with that, I want to wish you all a very Merry Christmas and Happy Holidays to you and your families, and look forward to an outstanding new year together. So take care of yourselves and enjoy the rest of your day.
Thank you, everyone.
Thanks, Tom.
Bye.